Hello, and welcome to this ProboStat seminar, which today is about a new accessory, namely the 4-leg thermoelectric generator module test system. It allows you to test 4 legs of a thermoelectric PM couple on top of a support tube inside the ProboStat. If we first talk a little bit about normal thermoelectric power measurements or Seebeck coefficient measurements, they can be done in NOREX sample support tubes in a ProboStat, in a schematic setup like this, where you can measure Seebeck coefficient and also 4-point resistance at the same time. NOREX also has a SEBSYS system, which is a ProboStat and an instrument package bundle. Many people also like the ProboStat-based disk sample measurement setup, which is not provided commercially, but which you can find in this publication in a review of scientific instruments. There are many other brands also who make more dedicated instruments for Seebeck coefficients, like the UVAC system and Lindsay's and Metch machines. However, if we go to thermoelectric generator measurements, then most setups are custom made by either the user or the supplier, making them quite complicated and quite expensive. There is one commercial machine readily available. It's a Lindsay system that you can see here, where the sample is placed here on the top of this plate, and there's a hydraulic pressure on it and connections and measurements of accurate heat flow, so that you can calculate the power, the efficiency of the setup. It operates in ambient air. But the most important feature maybe of this is that it operates at moderate temperatures up to 300 degrees maximum. That's the big difference to the now available NOREX ProboStat-based 4-leg TEG system. While this one from Lindsay's can test entire generators with many legs, the ProboStat system is intended dedicatedly for 4 legs. Here you see 2 of the legs. This is now an accessory to a standard ProboStat, so that if you have a ProboStat already, you need some new parts, and then you can use your existing ProboStat. Or you can buy a new one and do this. The low temperature goes from room temperature, while the high temperature side goes up to approximately 1000 degrees centigrade. And you can operate with temperature gradients of up to 600 degrees in our estimate. It can operate in controlled atmosphere inside the ProboStat, although the main advantage here of high temperature thermoelectrics, in particular oxides, is that they are stable in air. Anyway, the controlled atmosphere is an advantage. It does not have any heat flow measurements, and therefore it is best to characterize the thermoelectric power, not efficiency, and it's good for studying the stability of materials and interfaces in operation at high temperature over time. How do we achieve the temperature gradient, the big temperature gradient? We do that by replacing the normal support tube in a ProboStat. Here you can see the pedestal of the base unit. There's the pedestal, and instead of a normal support tube, we have a steel tube, a closed steel tube that we screw on here using an O-ring seal. And then we insulate this with an alumina sleeve tube, an open alumina sleeve tube that sits on the outside that protects this steel tube from the outer high temperature. Here you can see the sleeve tube coming up, and you can see that the steel tube is flat, And there is a inner tube to this steel tube that flushes the steel tube with water. You can either fill up the steel tube and let the water flow over the rim and down the supply tube, or you can in a way flush with a stream of water directly onto the flat part here with the water coming up this way. We think both work quite well. Then we build a module on top of this flat part here, on top here. And then we use a spring load, which we don't show here yet, to press everything down and keep electrical contacts. We use some small parts here to keep the legs apart. The high temperature is provided by a normal tubular furnace outside of the outer tube of the ProboStat. You can control now the high temperature either with the thermocouple in the furnace or with the thermocouple that sits here on top of the legs. Typically, the furnace will go up to a maximum of 1100 degrees, maybe on the outside, and the water temperature inside here will go up to maybe 100 degrees and start close to the boiling point, but preferably not boil. And then you would get something like 1000 degrees at the top here of the legs, and you would get something like 400 degrees here at the bottom of the legs. There is a very big temperature gradient through here in this case, so that you have a temperature gradient over the legs of 600 degrees, the temperature gradient here of about 400 degrees, and up here of maybe 100 degrees. But this works. Here is a close-up from a publication that we'll come back to of how it looks. You can see the sleeve tube coming up here, the steel tube here, the water supply tube here. There is a bottom disc here that keeps everything under control, that allows the wires to come in and out and things like that. Then we have the 4 legs, and we have a top plate that has the same function as a bottom plate here. Then we have like a piston, and then we have the spring load up here. And you can see some grooves here. That's for the thermocouples to go down to the top plate here to measure the temperature there. You can see that the whole thing sits inside the house, a housing that is indicated here. And you can see that we can build that up by rings so that you can build it to any height. So that the height of these legs can be from quite short, pressed down by the piston, to quite long if you build it up with 2 or 3 rings. These rings are made of machinable alumina silicate. If we look a bit more on the materials here, as I said, the housing, this part here, is made from a machinable alumina silicate that we machine. And then we have the top and bottom plates. Here you see the bottom plate with some gold contacts before we put on the legs. They are made from aluminium nitride, which conducts heat well, but is insulating for electricity. Then it has an alumina and platinum spring load, a standard spring load from the ProboStat. It has an outer tube around the whole thing, which can be quartz or alumina, for instance. It has this alumina sleeve tube sitting here, and then it has the stainless steel closed support tube inside. And we can use gold contacts for contact to the 2 legs here. And then there is an interconnect that connects the 2 other legs, and it's the other way around on the top. The thermoelectrics is, of course, from the user in order to test the materials. And this setup holds 4 thermoelectric legs. Each leg can be 5 times 5 millimeters of footprint, or smaller, but not bigger. And the height is flexible, as I said. The interconnects that connect the legs to each other are also in general user supplied. Here you see how we tested some gold interconnects after use. They are quite worn by the high temperature over a long time. So we use 2 interconnects here and 1 down here. And here you can see some ceramic cross that keeps the 4 legs apart that we also machine out. And I think quite important for this module is not only to test the materials, but also to test the interconnects, because the challenge at high temperature for high temperature thermoelectrics is just as much the interconnects as the material themselves, the stability and the contact to the legs. So these interconnects can maybe be gold, or it can be a cermet made between the leg material and metal, like silver, or it can be a composite of the P and N type materials, so that you enhance the contact area between P and N to lower the resistance of that junction. Here are some drawings of the small parts that you need to assemble this. Here is the housing ring. Here is the cross that keeps the 4 legs apart. Here is the piston that presses it down. You can see some features here, like these small holes, and there will be a corresponding thing that goes into it here on the other side, so that you can put several of these together. You can see how the cross goes into a groove here to keep it in place. Here are the 2 plates, the bottom plate and the top plate. You can see the groove for the thermocouple going through here to pick up the temperature as good as possible at the bottom of the legs. And similarly, a thermocouple comes in here and goes down and goes here to the top plate and tries to measure as good as possible the temperature at the top of the legs. And here you see how these 5 parts are assembled in order: the bottom plate, the rings, the crosses, the top plate, and the piston. The module has been used in one paper that you can read if you find this of interest. It's a paper by Rafael Schuler and Reshma Madatil and me, published this year. It is essentially a paper that reports the use of this test module. Here you can see from this paper, as a function of the furnace temperature going here, you have various temperatures on this scale. Here you see the cold temperature. This is the temperature inside the water. It remains cold. Here is the temperature at the bottom of the legs. It gets warmer when the furnace gets warmer. Here is the temperature at the top of the legs. You can see when the furnace is at 900 degrees, the top of the legs is at something like 850 degrees. So the gradient up there is not so big. And here you can see the total gradient then is the difference between these, and that is the green line going here. So for this case here, at the hottest temperature here, you get a temperature gradient of about 540 degrees. We used the setup to test a generator made of lithium-doped nickel oxide and aluminium-doped zinc oxide. We used a gold foil and we used silver paste to make a contact between the legs and the gold foil. So we measured the open circuit voltage and the resistance of the generator and the maximum power. And here you can see them plotted as a function of the temperature gradient through the generator. And here is the high temperature on the top of the legs. plotted at the same time. Here we can see the open circuit voltage during heating and cooling. And here we have the power, goes here up to 10 milliwatts. And here you see the resistance of the system is going down as the temperature goes up. We also are interested in the stability. Here you see the voltage of the generator at 25 milliamps of constant current at the top temperature of 630 degrees and a gradient of 430 degrees. And you can see that the voltage doesn't change that much, but in the beginning it goes up, which is a good thing. And we think it's because you're making better contact when the materials get soft and they come together. And then it starts degrading because of various processes that are discussed in detail in the paper, connected to the interfaces between the different materials, like the paste and the leg. Here is another paper on a silicide thermoelectric and using not the same module as I showed you now, but it uses the same steel tube with water inside as the cold source, and then it uses the furnace heat around here as the hot source, and that generates a gradient over the legs. In this case, the maximum temperature is only 250 degrees, so you don't need all of that insulation to protect the steel from the furnace. And that was all. If you have any questions or comments or inquiries, feel free to contact us.